Okay. Hello. Welcome to the lecture. So, so in this talk, in this lecture, I will talk about the Witten diagrams and their Mellin transform. Their Mellin transform in the content of a Adslt duality. Okay. So let me begin by a brief introduction about the Adslt duality. So ADS, CFT, duality. So this is a duality between two seemingly very different theories. So on one side of the duality, we have quantum gravity. It's a quantum gravity on anti-de Sitter space. So anti-de Sitter space-time. Say in d+1 dimensions. So we will denote it as AdS d+1. And on the other side of the duality is a d-dimensional conformal field theory. So we will denote it as a CFT. And the conformal field theory lives on the boundary, the conformal boundary of AdS space. As I emphasized, so this is a duality between, again, two seemingly very different theories. One is a quantum gravity, and the other is a conformal field theory. Okay. So Adiactive Duality was first proposed by Marasina about 2 decades ago, 1997. So this is a concrete realization of so-called holographic principle. Holographic principle. So since we have a dual between a theory on living on d+1 dimensions and the theory living on the boundary in the d-dimension space. Okay. So there are a few very well-known examples of Adslt duality. So let me mention some of them. So well-known examples of Adslt duality. So the first example, I think this is one of the best studied example of Adslt duality, where on the supergravity, on the quantum gravity side, we have type 2b superstring theory on the background of AdS5 cos S5, whereas on the and it was conjectured this theory is dual to a 4-dimensional conformal field theory. It's a supersymmetrical conformal field theory. So the theory is a Yamil's theory. With N4 supersymmetry. Okay. So yeah, so it's a Yamil theory with maximal supersymmetry, and turns out this theory is a conformal invariant. Another example is where we have M theory on AdS 4 cross 7. So remember, M theory lives in 11 dimensions, and the dual theory lives on 3 dimensions. So it's a 3-dimensional conformal field theory, again with the supersymmetry. So it's a 3-dimensional. It turns out it's a 3-dimensional super symmetric Chern-Simons theory. So in 3 dimensions, it's natural to define a Chern-Simons theory. Simons coupled with methods. So it's called Chern-Simons method theory. Also often known as ABGN theory. The final example where we have M theory. Now on AdS 7 cos S4. And the dual theory is a 6-dimensional super conformal field theory. So super conformal field theory with 2,0 supersymmetry. Okay. One important aspect about Adiactive duality is that it's a weak, strong duality. So let me see. So say weak and strong duality. So namely, when the fields in say in conformal field theory are strongly coupled, and the dual ones in quantum gravity are weakly coupled, and vice versa. So therefore, the duality provides a very powerful tool for study strongly coupled quantum field theory or strongly coupled conformal field theory, and well, of course, also provides a very useful tools for understanding deeper lessons about the quantum gravity. Okay. Let me now introduce these 2 main players of this lecture, namely conformal field theory and AdS space-time. So let's see some basic aspects of CFT and AdS space. Okay. So given the time constraint, we will be a bit brief. So conformal field theory is a quantum field theory that is conformal invariant, and so conformal symmetry say act on the space-time coordinates, setting x to x prime. What it does is that it leaves the metric almost invariant up to an overall factor. So we will consider the conformal field theory as a flat space, a Euclidean flat space. And so what it does is that it changes the metric to say G nu nu. Well, let me just. So changes the metric. Original metric is a Euclidean space, so delta nu nu, to a new metric, which is, as I said, it's overall factor times the original metric. We can call G nu nu. X prime. And so it's known that the conformal symmetry is an extension of the Poincare symmetry. So this is one. So there's another way to extend the Poincare symmetry is by introducing fermionic generators that leads to famously that leads to a supersymmetry. So conformal symmetry, as I said, is an extension of Poincare symmetry. Therefore, it contains Poincare symmetry, which we can denote translation, rotation and the translation. Okay. The additional symmetry, the extension to Poincare symmetry, includes dilatation. Dilatation, often denoted as D. What it does is really a scaling. It's a scaling symmetry. So set x to x prime by scale a factor. Another one is so-called the special conformal symmetry. We will denote it as a K. What it does is that it takes x to x prime, and so this is nonlinear transformation. X prime takes the following form, whereas A is a transformation parameter. Okay. So the special conformal transformation looks a bit complicated. However, it can be generated by a combination of simpler transformations. So it turns out it can be generated by following combination. First, you do an inversion, which takes x to basically 1 over x. Then you do a translation. So by this parameter A, then you do another inversion. So plus another inversion. Okay. The statement is that the combination of this three action gives you the special conformal transformation. So those are symmetry generators. I denote here. Well, of course, rotation and the translation and the dilatation and the special conformal transformation for algebra, so conformal algebra. And then you study the commutation relation between them. They should close. Let me list a few of them. So in particular, the commutation relation between dilatation and the special conformal transformation goes back to leads to K itself. And similarly, when D commute with P, goes back to P. So these two are almost the same up to a subtle sign difference. We will come back. Another one maybe is the commutation relation between K and P. So it's a tensor where you can say decompose into a symmetrical part. Turns out it's proportional to D, and the anti-symmetrical part, which is simply the rotation. So there's a few more commutation relations. Okay, so One important aspect about the conformal field theory is so-called state operate correspondence. Namely, there's a one-to-one correspondence between a local operator and a state in a CFT. So suppose you have a local operator, let me call O. There's a corresponding state, which can be defined as, say, using, say, Dirac bracket, which is defined as this O at origin acting on vacant state. Right, vacant state. Okay. So as I said, so this is correspondence is one-to-one. Those states are eigenvectors or a dilatation operator. So namely, so say D acting on a state has eigenvalue delta. So for those states, I denote as O delta. Or in the language of local operator, the commutation relation between this operator at the origin. Let me separate them a little bit. Is given by delta times this operator. So, namely, those operator as a, from eigenvector of the dilatation operator, and I'm sure you know that this delta is a so-called conformal dimension of this operator of this state, conformal dimension. Okay. So those operators and the states can be separate into two classes. Say there are two types. One is called primary or primary operator, primary states. The other is called descendants. Descendants. Okay. So basically, the statement is that the primary operator are those cannot be written. So they cannot be written as derivative acting on other operators, other local operators. Okay. Whereas descendants can. So descendants can be written as derivatives. Okay, they can be written as derivatives acting on other operators. Okay. Using those generators, so the primary operator are defined as those operators which annihilate states annihilated by special conformal transformation. So the primary operator, well, of course, as I already said, they are eigen states of a dilatation. So that's the primary operator. Okay. Or in the operator language, so the commutation relation between K and O at the origin vanishes. So from this we see that a primary operator is really, according to the name, is more primary. More since descendant operators are simply dilutive acting on other operators. So once we know like primary operator, we really know about descendant operator. They are generated by derivatives acting on primary operator. So therefore, we will simply focus on primary operator only. So another important aspect is that the generator K mu really plays the role of annihilation operator. Annihilation, whereas P mu plays the role of creation operator. So this you can see from the algebra, and as I mentioned, this crucial sign difference, basically very much the same as what you see from harmonical oscillator. Right? So therefore, K mu basically decrease when the action of K mu on the operator decrease the dimension. So let's see what the K mu does. See, if you have a operator with a conformal dimension, I don't know, say delta plus 2, the action of K mu basically reduce it to operator with delta plus 1, and so on. So the action will just reduce the dimension, and until it became a primary operator, and the action of K mu annihilates it. Okay. Whereas the action of P mu does the opposite, right? So if you begin with a primary operator, P mu will turn it into a descendant, since P mu really is simply a derivative, but it increases the dimension. So again, so if we continue to act it will increase, and so on. Okay. All right. So right, as emphasized, so we would simply study primary operator, and the property of descendant operators can be reduced, can be deduced from the property of primary operators. So let me give you some examples. So the physical observable in a conformal field theory are correlation functions. Okay, so let's say for simplicity, we will simply focus on scalar operators, so operators that has no spins. So it's known fact that conformal symmetry fix 2 and 3 point functions, 2 and 3 point correlation functions. Okay. Functions, say, of local primary operators. Primary. And I said we will just focus on scalar. Yeah. Okay. So turns out 2 point function, as we said, say I have operate a scalar operator with a dimension delta 1 at the position say x1, and another operator with conformal dimension delta 2 at the position x2. The correlation function, as I said, is completely fixed by the conformal symmetry, and so up to normalization, the result is given by canonical delta 1, delta 2. So this canonical delta implies that this correlator is vanishing unless delta 1 is equal to delta 2. And here x1, 2 is really means x1 minus x2. Okay. Similarly, at 3 points, again, as I said, the symmetry fixes completely up to a constant. This constant can be non-trivial function of your theory, say depends on coupling, or even depend on say if you're considering a gauge theory like N4 Mills, so it may depend on the gauge group, say it's SU and gauge group, and so on. Okay, but doesn't depend on space-time, namely does not depend on x1, x2, x3. The space-time dependence are completely fixed. So this is given by x1, 2 square, delta 1 plus delta 2 minus delta 3 divided by 2, x1, 3 square, delta 1 plus delta 3 minus delta 2 divided by 2. And similarly, it's 2, 3 square, delta 2 plus delta 3 minus delta 1 over 2. Okay. Now begins from 4 points. The conformal symmetry cannot fix the correlator uniquely. However, so for instance, at the 4 points, let me simplify the story. Say, consider the operator with a single dimension. 2, 3, 4. So now, well, it's a function of x1, x2, x3, x4. However, conformal symmetry fixes it to be as a function of 2 variables. So you can take out some factor which take care of say conformal symmetry. So this factor basically is required for this correlator transform properly under conformal symmetry, and what's left over is a function, unknown function of cross ratios, so-called cross ratios. U and V are the cross ratio. So U is defined by x1, 2 square, x3, 4 square over 1, 3 square, 2, 4 square. And similarly, V is equal to U with 2 and 4 exchanged. So indeed, so at the higher point, conformal symmetry cannot fix the correlator, but still, nevertheless, it simplifies a lot. In the 4-point case, it's a functional, make a function of 2 variables only. Okay. All right. Now, so let me say a few words more about the conformal field theory. In fact, we will introduce something relevant for the computation of Witten diagram. So first is observation. In fact, can trace back to Dirac. So it turns out that the conformal symmetry, so which include the Poincare, dilatation, and the special conformal transformation, they together actually is isometry. So conformal symmetry in D dimension, so D-dimensional conformal symmetry is isometric. Isometric is equivalent, basically. It's equivalent to SO D plus 1, comma 1, which is the Lorentz group. So this is simply Lorentz or D plus 2 dimensional Minkowski space. Okay. So the point that the generator OSO D plus 1, comma 1, say, can be, so let me write the coordinate of this space as a capital X, say XA, where A run from 1, sorry. So let me just, yeah, A run from 0, 1, 2, D and D plus 1, where this I will call mu, where the D-dimensional conformal symmetry lives on. So the Lorentz generator, let's say it's a rotation, let me call J. So it's JAB. Well, it's given by, say, minus I XA 02 is XB anti-symmetrized. Okay. And so the point that this generator J can be identified with the conformal generators. So obviously, so J, when A and B are living on this D dimension, so in the mu, so J gives you the D-dimensional Lorentz generators, where, so this is, so, okay, let me just write this out. So this is identified with J mu mu. And when A and B living on 0 and D plus 1, this gives a dilatation. So here's the identification. And well, then obviously we need a vector in D dimension, so which is one is the special conformal transformation. So this is given by J0 mu plus JD plus 1 mu, and the translation is then given by the difference. Okay. That's it. So indeed, well, basically we see that the as I said, the D-dimensional conformal symmetry you can obtain from SO, the D plus 2 dimensional Lorentz symmetry. So this idea leads to so-called embedding formalism. So what do we need to do now? Because we are living in D dimension, so we want to basically embed our so the idea is that we want to embed our D-dimensional space in this D plus 2 dimensional space. Okay, and we are D plus 1. So roughly speaking, we need to impose two conditions, and those conditions should naturally presume the this Lorentz symmetry. So one of them is basically simply it's simply the light rate. So the light, so for those coordinates, I will call P now. So we will require this D plus 2 dimensional coordinates obey the light condition. So these are, let's say, light rays. So this condition, of course, is a Lorentz invariant. And additionally, we want to impose a quotient. So we want to quotient it by a scaling. Okay. So we can parameterize this D plus 2 dimensional coordinator. Here I call it P. So the D dimensional coordinator X can be identified with P as following: P plus, where P plus is P0 plus P D plus 1, the light cone condition direction. Okay. Yeah, so this ratio makes the scale invariant, right? It's invariant under this quotient. So a natural parameterization is that the P takes the following form. So P0 equal to, say, 1 plus x squared over 2. P mu is equal to, well, x mu. And P D plus 1 then is 1 minus x squared over 2. Okay. So easy to see, this obeys the light condition. Okay. Right. Okay. So due to this quotient, so now we want to define my operators, especially the primary operators, in this P space, in this D plus 2 dimensional space. So due to this quotient condition, so the primary operators is so defined in say this P space, the embedding space. Well, yeah, embedding space. Embedding space. So we want to define this operator in embedding space. So I want to define it in embedding space. It should have the property where should have the homogeneous property, namely when I rescale the P, the operator should obtain an overall factor which is related to well, basically related to the related to the conformal transformation. Okay. So the requirement is that we want the operator has a homogeneous property. Okay. So now, and with this setup, the conformal symmetry constraints basically becomes a, so this becomes this become D plus 2 dimensional Lorentz symmetry plus this homogeneity condition. All right, so let me use this language to write the correlation function. Okay, so let's see. Say again, so I want to compute to write the 2-point function. So say I have operator with dimensions again. So we will just consider scalar operators with dimension delta 1 and the dimension delta 2 in this embedding space. So as we said, this should be Lorentz invariant. The Lorentz invariant must be P1 dot P2. That's the only thing you can make up because P1 square equal to 0 because it's light like. Right? It's light. So the only invariant you can make up is the P1 dot P2. Then this scaling requirement uniquely fix it. Well, not surprisingly, so two-point function is fixed. So up to overall factor. So it's fixed to be, and again, so this is non-vanishing only if delta 1, delta 2 are equivalent. And similarly, at 3 points, again, the Lorentz symmetry requires it's a function of P1, Pi dot Pj, and the scaling property requires basically uniquely fix the answer. So up to, again, a constant. So the result basically is P2 delta 1 plus delta 2 minus delta 3 over 2. Well, I'm sure you know what's the answer. So it's delta 1 plus delta 3 minus delta 2 over 2. And this finally, sorry, let me move it a little bit to the other side. We have minus 2p2 dot p3 delta 2 plus delta 3 minus delta 1 over 2. Okay. So compared to the previous answer, they are identical. To see that, one need to use the effect that the 2 minus pi dot pj is basically xij square. So this you can see by using this parametrization. It's easy to see that. Okay, just plug it in, and you will see pi dot pj is simply xij square. Okay. All right. So you, as I said, so using that, then you see this answer reduced to the one we loaded out previously in coordinate space, those ones. All right, so here we basically finish a very brief introduction about the conformal field theory and the use of embedding space, which will be relevant for computing Witten diagrams. So how I do with the time? Okay. Now let me introduce the other players, namely the AdS space-time. So AdS antecedent space time. So it's a solution to Einstein equations with negative cosmological constant. Constant. It's a maximal symmetrical. So it's a maximal symmetrical d plus 1 dimensional space. This can be thought of as a hyperbolic. Sorry. Namely, so say, let me call the coordinate as x, a. Again, so a 0, 1, d plus 1. So we have x0 square plus x1 square plus xd plus 1 square equal to minus r square, whereas r square, so this is a radius of AdS space. And we will, well, in our discussion, we will simply set r equal to 1. Okay. So this is a hyperbolic embedding in a, so embedding in d plus 2 dimensional space. Okay, well, a natural parametrization can be, we were using, can take x0 equal to, so 1 plus x square plus z square over 2z, and x mu is x mu. So the little x is the, so the little x and the z form a d plus 1 dimensional space of the AdS d plus 1 divided by z, and the x d plus 1 is simply 1 minus x squared minus z squared minus 2z. So this parameterization often called Poincare coordinates with a metric. So the metric can be written, well, using this. The metric is given by dj squared plus delta mu dx mu divided by z squared. Okay. So the boundary, the conformal boundary is at z goes to 0. Okay. So we can see that when z goes to 0, x. So at the boundary, I would denote it as a p. And so up to overall, so up to overall scaling, p is simply equal to, say, p0 equal to 1 plus x squared divided by 2, and p mu is simply x mu, and p d plus 1 is simply 1 minus x squared divided by 2. So here, up to a scaling, up to a factor of z, basically, right? So I literally take this guy and setting z to 0. Look at the case where z is small, and up to over factor z. But of course, you see this p before. It is the, so, well, in particular, you can check, well, we see, as I said, we see p before, and in particular, p squared equals to 0. So at the boundary, the boundary AdS is precisely the embedding space we introduced previously. Okay. What else? Right. So one more thing. So AdS d plus 1. Well, it's obvious, has isometry. SO d plus 1, comma 1. And as I said previously, SO d plus 1, comma 1 is precisely, which is precisely the conformal symmetry in RD. So therefore, well, this is like one of the important indication of Adslt duality. Why ADS has anything to do with the conformal field theory? Okay. All right. So how I'm doing with the time? So let's finally start to look at the Witten diagrams. So Witten diagrams. So I should finish. Well, basically, Witten diagrams, they are Feynman diagrams. In ADS space, in ADS. Okay. A typical Witten diagram looks like following. So here, so first I will represent ADS space as a disk where, so let's see, where, so this interior will be like the bulk of ADS, and the boundary is the boundary is the boundary of ADS. Okay. So a typical diagram looks like, say, something like this. Where, so say this is a 4 point where I have 4 points living on the boundary, and so these propagators, there are two types of propagators. One type, let me use a different color. So one type like this one. So this is going from a bulk point to a boundary point. So this is called, say, bulk to boundary propagator. Often I would denote well, say the bulk point is X, capital X. So bulk point we often denote as a capital X, and the boundary point denoted as a P. So this we will often denote as a K, say from bulk to boundary. For a state or for operator with a conformal dimension delta, so we denote like delta below. Then we also have this propagator, say from X to Y. So this is so-called bulk to bulk propagator. So it's a bulk to bulk. And I will denote as G. So again, say it's a propagator or operator with dimension delta. So it's going from, say, X, going between X and Y. And so besides those operators, we also have interaction vertex, like here and here. So those are vertex. So indeed, so this is exactly the same ingredient you have for a Feynman diagram, propagator and the interaction vertex. Well, the only difference is that we are living, instead of a flat space, we are in a curved ADS space. And that leads to the fact that the vertex and the propagators are more complicated. Okay. So those propagators or the operators can be scalar, vector, or spinors. So we will consider basically the simplest case, the scalars. So we will consider, say, a model, a scalar model, say, action in ADS space. So we integrate over ADS space. with some AdS coordinate. The action say has, as I said, so we will consider a scalar theory with some mass. Okay. So this are the interaction terms. They can be, say, lambda phi q or lambda phi 4, etc. Okay. Such a model often people call they can be singled as effective field theories in AdS space. Okay. And so not surprisingly, so the back to boundary, sorry, back to back propagator is determined by back to back propagator propagator G is determined by the Laplacian equation. So where we have Laplace minus the mass equal to delta xy, and this delta is it's a delta x minus y defined in AdS space. Okay. The solution is given by a Bessel function. Sorry, hypergeometry function. We're not talking hypergeometry function. Well, so first of all, delta x is given by square plus x dot x. So use this, one can solve the differential equation and find that G is given by some normalization factor times u, I would say. So u is defined by x minus y squared. Okay. And it's a hypergeometry function. Delta minus h plus 1/2. 2 delta minus 2h plus 1 minus 4 over u, where h is the half of the dimension d. Okay. So we will not really use this formula. We will use, well, we will introduce another representation, but nevertheless, so this is a result of the back to boundary propagator. Now we need also back to boundary propagator. So to do that, one way is to do that is by pushing. So back to boundary propagator is basically is a limit of back to back propagator by setting one of the point to boundary. So we can set, say, y to boundary. To do that, we can set y to lambda p plus something else. Well, so the point is that there's something else do not grow as lambda go to infinity. So the purpose of this something else is just to make sure y squared equal to -1. Okay. So now we can take a lambda to infinity. Okay. So the back to boundary propagator. So I called xp can be given by limit, where we take lambda to infinity, lambda minus delta. Sorry, lambda not minus delta, minus lambda delta with the back to back propagator. So we set y equal to lambda p plus something else. So in this limit, it's easy to see that u basically goes to infinity. So therefore, the argument of Bessel function goes to 0. Therefore, Bessel function equal to 1. Then you can see that this is simply given by c delta divided by So let me see how I divided by minus 2p dot x to the power delta. Okay, this coming from this factor. We will actually write this in a Schwinger representation. So, this can be rewrite. Sorry, whereas I didn't tell you the C. So sorry. So C, the normalization here is given by gamma delta divided by 2 pi h gamma delta minus h plus 1. Okay. Okay. So with that, and write this as a Schwinger representation. So this is given by 2 pi h over gamma 1 plus delta minus h. So Schwinger representation t to the delta e 2t p dot x. So we will see why we want to write it in this form. So the back to boundary propagator is obviously much simpler than the back to back propagator. And as we said, it's a limiter of back to back propagator when you set one of the point to the boundary. It turns out there's another interesting relation between back to back propagator and the back to boundary propagator. In fact, one can rewrite the back to back propagator in terms of back to boundary propagators. So this formula will be very important when computed Witten diagrams with back to back propagators. Okay, so the formula takes the following form. So there's an identity C 2 pi I with some function. Let me just not introduce this additional function. So it's simply 2c squared divided by c squared minus delta h squared. Then there is integral over some boundary point. Let me call P. So this is on the boundary of AdS. Then I have a 2 back to boundary propagator with the dimension h plus c. So this is from x to p. Then another back to boundary propagator from y to p. So diagrammatically, so we have back to back propagator from position x and the y. This is given by, as we said, integration over c. So let me call this as say g delta c. So g delta c. Then I have integration over a boundary point, p, and so this basically break a back to back propagator into 2 back to boundary propagators. Okay, so this, as I said, is a very useful formula for the computation. All right, in the final 30 minutes, let's do one simple example of Witten diagram, and I will leave slightly more complicated ones as exercise. Okay, so we will consider, well, as I said, this is the simplest one, the 3-point Witten diagram. So say I have P1, so 3 boundary points P1, P2, P3, and a back point X3. So this is coming from lambda phi q interaction in AdS. We want to compute this diagram. All right, let's denote the correlator as say, I don't know, let's call A, P1, P2, P3. Sorry. Well, so say it's coming from a lambda phi q, so this is proportional lambda, and it's given by product of 3 back to boundary propagators. So we integrate over this back point. Exactly what you would do in flat space. So then I have K. So suppose each has a dimension delta 1, delta 2, delta 3. Okay. So K delta 1. So this is propagator from P1. So X to P1. Then another one. So X to P2. X to P3. So that's all. Well, so the procedure is very simple. Now you just plug in the definition of back to a boundary propagator, which is given by here. Here, so as I said, we will. It's convenient actually to use Schwinger parametrization. Let me copy it. So let me just copy here. So how I do it? Okay, let me make it smaller. Okay, so this is equal to so how I'm doing? Okay, I'm doing okay. Well, let me move it here, and I can see it. So this is equal to so basically equal to lambda. Well, let me forget the lambda. So we will put it back at the end. So we integrate over x. Now just plug in this result for each propagator. So it's a bit tedious. So in fact, let me just take this factor out. So 1 over 2 pi h gamma 1 plus delta I minus h product I from 1 to 3. Okay. Then we have Schwinger parametrization. So we have the Ti over Ti, Ti delta I. And so again, so this is a product I from 1 to 3. Then I have E 2 Ti Pi. So sum over I 2 dot x. Okay. So here we really didn't do anything. We just plug in the definition of the back to boundary propagator. So I won't need it anymore. Well, so the reason we introduced this Schwinger representation is because it's convenient. In this representation, we can do the AdS integral first. Okay. So to do that, we need to use a integral identity, which I will give you as an exercise. So so use. So if I have integrate over AdS space of object like E say 2q dot x. So here q is basically this guy. The result is given by pi to the h as usual blue integral dz over z minus h minus z plus q squared over z. So where z, remember, is the parametrization of this AdS space. So it appears here, okay? So use this identity. Let me box here. Then we have, so I have, well, let me just copy it. We have this prefactor, then so now I done the AdS integral. So I have I 1, 2, 3 d ti over ti. So I have ti delta I. So after the integral, so I got the z integral to do 0 to infinity dz over z. Well, there's a pi to the h. So let me just take that out, pi to the h. Then z minus h minus z plus q squared. So where q is this, so, well, q is this object. This square is simply sum over ti tj pi dot pj twice over z. Okay. Because each pi square is 0, so you only have I smaller than j. Okay, I hope you can see it. Okay, so then, well, now to do the z, now we can do the z integral by rescaling. So say after rescaling ti, let me change the color. Say if we set the ti go to ti square root of z, do the scaling, then you will find that, okay, so first of all, I have this constant. Well, again, let me just copy it. Sorry. Copy, paste, let me make it smaller. So do the rescaling and do the z integral. So the z integral can be done easily now. So you will find, right, so actually, well, actually, so, okay. So I would do the, so as I said, do this rescaling, then do the z integral. The result is, so pi to the h. So this, I think this is a result of, so this is sum over I equal to 1 to 3. So then I have this prefactor again, 2 pi h gamma 1 plus delta I minus h. Now after the z integral, we left with t integral, which takes the following form. Ti tj pi dot pj. Okay. We're almost the end. So to do the t integral, we will use the so-called another integral identity, which I'll give you as an exercise again. So use so-called Zemansky, sorry, Zemansky star formula. Zemansky star formula. In general, so again, so as I said, this will be exercise. And this will be exercise. No, sorry. So the formula in general, so if I have a bunch of t integral like this one, say m of them, ti over ti and ti delta I, with again, so it's a say ti tj pi dot pj. Is given by another integral, go with gamma. So I will explain what are those guys. So the integration is around the contour, say minus I infinity to infinity plus some shift. So this shift is just to avoid the poles of those gamma functions. Minus 2 pi dot pj minus gamma ij. Okay. So here, so I should make it clear. So sorry. So here the integration dimension is over. Sorry. What I should do now? So let me just move this whole thing a little bit to this side. Let me clear up and so make it clear. So 1/2 integral, say for the minus I infinity to infinity plus some shift. And the integration is for I smaller than j. So it's a product I smaller than j. So that's because gamma ij has some constraints. So gamma ij is a symmetric, basically, if you want. So therefore, we only integrate over I smaller than j. And furthermore, it's constrained sum over gamma ij for j not equal to I equal to delta I. So where delta I is the conformal dimension. So use this identity. Yeah, as I said, an exercise. So then we can translate this integral into a gamma integral. Well, okay. So basically, this is now. So let me just go to here, and the result is okay. Let me copy the prefactor. Copy equal to the prefactor. Equal to the prefactor times 1/2 integral over gamma. So I is smaller than j, d gamma ij over 2 pi I. So I is smaller than j until 3, right, in our case. So it's gamma function, gamma ij minus 2 pi dot pj. Okay. And as I said, so with the gamma ij, satisfy this constraint. Satisfy this constraint. Okay. Okay. So this is basically the final answer of the correlator we want to compute. So I call it A, P1, P2, P3. So let me draw the diagram again. The Witten diagram. So before we finish, let me make a few comments. So comments, say the first comment. So in this case, as we said, so gamma ij is constrained by this condition. So well, so write this out. What this means? So this means, say, gamma 1, 2 plus gamma 1, 3 equal to delta 1, right? So gamma 1, 2 plus gamma 2, 3 equal to delta 2. Gamma 1, 2, sorry, gamma 1, 3 plus gamma 2, 3 equal to delta 3. So well, we have 3 unknowns, gamma 1, 2, gamma 1, 3, gamma 2, 3, and the 3 equations. You can solve them. Well, so so from here, we find, so gamma 1, 2 is simply delta 1 plus delta 2 minus delta 3 minus 2 over 2. Gamma 1, 3 is delta 1 plus delta 3 minus delta 2 over 2. And the similar gamma 2, 3 is delta 2 plus delta 3 minus delta 1 over 2. So they are completely fixed. So at 3 points, there's really no integral. So they're fixed. So plug this into A3. So basically, you can plug this into A3. Well, up to those overall factors, the Pij dependence, the space-time dependence. Sorry, I think it's the height. The Pij dependence it only appears here, and once you plug it in, then so we find A, P1, P2, P3 is proportional to minus 2 P1 dot P2 minus delta 1 plus delta 2 minus delta 3 over 2 minus P1 dot P3 minus delta 1 plus delta 3 minus delta 2 divided by 2. The last term minus 2 P1 dot, so P2 dot P3 minus delta 2 delta 3 delta 1 divided by 2. I hope you can see it. And this answer is precisely the one I show you when we introduce the embedding space. Okay, so indeed, as we said, the 3-point function is completely fixed by symmetry. So the computation better reproduce the known result. Okay, that's one comment. The second comment, the answer is written. So I said I stop here as the final result. The reason is that the final result is naturally in a Mellin space. So this is precisely the inverse Mellin transformation, inverse Mellin transform. So in general, yeah, as I said, the 3-point result. Is naturally in Mellin space. Okay. So in general, say I have an n-point correlator. Say n-point correlator for operators is, again, scalar operators with different conformal dimension. Let me do embedding space. So P1, P2, and so on. Delta M, Pm. They can always written, it turns out, as a inverse Mellin transform, written as exactly the formula we have been writing, divided by 2 pi I times, well, let me put it down here. Times, sorry, times minus 2 pi dot pj minus gamma ij, gamma function, gamma ij, and times some function called m gamma ij. Okay. And again, so gamma is a symmetric, and the constraint, exactly what I said before. I didn't say this before. So when you have such a constraint, well, it turns out that it's natural to write. So one can naturally write gamma ij as a product of vectors, say ki dot kj. So, well, obviously this will have symmetric, and if ki kj obey following conditions, so sum over ki, so they are kind of vectors 1 to m equal to 0, and the ki square equal to minus theta I. So this condition makes sure this is satisfied. Well, so this looks familiar indeed. So ki really plays the role of momenta, so ki plays the role of 0 of momenta, and the gamma ij, well, plays the role of Mandelstam variables. And well, this introducing this ki and point out gamma ij is like Mandelstam variables. We would really want to say this mij will play the role of scattering amplitudes in flat space. So mij is often called the Mellin amplitude. Okay. So the important point that the mij, well, the reason it's called the Mellin amplitude is really because mij has basically all the property of scattering amplitudes in flat space you know about. So in particular, one particular point is that so remember AdS space, one can take a so-called flat space limit. So namely, we can take the radius of AdS to infinity. So let's say take to infinity. Therefore, the AdS became a flat space, and the statement is that in this flat space limit, the Mellin amplitude reproduce the flat space, well-known flat space amplitudes. So in the example we did, basically the simplest example we did, well, again, so this is 3 point. So we see the Mellin amplitude of this case is really just 1, right? I mean, times 1. Well, if we put it back as the coupling lambda, so it's basically lambda. So as I said, so for this case, the milling amplitude is simply lambda, which is what you would expect it, because it's a lambda for amplitude, because we are talking about lambda phi q theory. The amplitude is lambda, not surprising. So another important point, as you can see, when I define the milling amplitude, I factor out this gamma function part, right? So I mean, another milling inverse milling transformation would take these two together, but I purposely factor out this gamma function. So one reason is that only after you factor out this gamma function, what's left over, I call m here, behave like amplitude. So in this case, say the simplest case, after you factor out the gamma function, we're left with 1 or lambda, and that's namely that's the result of the lambda phi q theory. Another reason for factor out the lambda is that so in conformal field theory, that's so-called operator product expansion, or OPE. Namely, you can put the two operators very close. So say if you look at the 4-point correlator, when you put, say, these two very close, they can describe by exchange another operator. So this reflect in correlator as some singularity. Okay, and this singularity so here I'm talking about in coordinated space. So this singularity is reflecting poles in milling amplitudes. So namely the say OPE singularity is reflect in poles in milling space. Of course, the gamma function has poles, but those poles are more or less trivial poles, and so in fact those poles represent the exchange here, the exchange also called double trace operators. So those are poles. So the poles in gamma j represents so-called double trace operator. So in larger n limit, the double trace operator, we basically know what are they, and in particular, the enormous dimension of the double trace operator are suppressed by 1 over n collections. So I didn't say, but larger n limited, the holographic theory, the AdS Duality, the dual conformal field theory is very natural by taking a larger n limit or do larger n expansion. So it's natural to factor out the contribution of double trace operators. Well, here in milling space, the information is contained in gamma function, and what's left over n, the milling amplitude, only contains more maybe let me say more dynamic information, namely the poles in the milling amplitude represents so-called single trace operator. Okay. Okay, so my time is almost up. Let me, I think, let me stop here. So I will see you next Monday for the live session. So I will, as you will work out for those exercise. We will look at in the exercise, we will look at the slightly more. So here in this lecture, we just look at the simplest case. So we will look at the slightly more involved Witten diagrams, and again try to compute the Mellin amplitude for those diagrams. And this structure I mentioned, say the Mellin amplitude has the property of scattering amplitudes, and the flat space limit of the Mellin amplitude is precisely the flat space amplitude. You will also again see it in those more non-trivial cases, although we see the indication, or we see the structure in this simplest case. Okay. Okay. See you next Monday. Bye bye.